Good afternoon, everybody. So my name's Kristin Bartik and I'm a chemist. So we're going to be changing fields a bit. And I'm going to talk to you not about hardcore organic chemistry, be reassured. We're going to stay with something very simple. I'm going to talk to you about water and the importance of water for life as we know it today, and especially to try and answer the question why water is so important, why it is always seen as the mantra for looking for life elsewhere is to look for water. So it's going to be scientific, a little bit philosophical as well, so to try and challenge your opinions about certain things. So to start off with, just talking about water and life on Earth today, there is no doubt that life as we know it today is based on the presence of macromolecules, so the storage of information, the transmission of information, playing the catalytic roles that is known by proteins, played by DNA and RNA. It is also based on the chemistry of reduced carbon. So over here you've got glucose, which is certainly one of the most important molecules as the fuel that we have being transformed afterwards into ATP, but it has to be reduced carbon. We're not going to have already carbon in its completely oxidized form. And here these are just illustrations of proteins and the double helix of DNA. But also water today, life on Earth water is very important for life on Earth today. If we look at it, it's present in all living organisms. Here seen as presence in 95% of water in the jellyfish, somewhere between 60 and 95% for all living organisms. Is a solvent of life. It's our solvent, whether we're looking at the saliva, the tears, the gastric fluids, urine, sweat, it's all water. And just to show you how finely tuned the living world is to water, if we were to drink heavy water, so just the isotope effect of replacing hydrogen by deuterium, it would be toxic. All our systems, all our proteins, all the metabolism would not be working efficiently just by changing water towards heavy water. So question now is, what about water and exobiology, astrobiology, however you want to call it. I've just come over here with, I'm going to show you 3 press releases which have come out from NASA, from 2000, the first one here from 2013, reporting Kepler's mission and the discovery of the planetary systems that include 3 super Earth-sized planets. And what's important, talking about the habitable zone, which we already talked about this morning, was the range of distance from a star where the surface temperature of an orbiting planet might be suitable for liquid water. And a little bit further down in this press release, you can read, scientists do not know whether life could exist on the newfound planets, but their discovery signals we are another step closer to finding a world similar to Earth around a star like our sun. So the notion of water, possibility of finding life. Another press release, 2016, with NASA's Hubble, which spotted the water plumes coming from Europa. Over here, the representation coming from a blog where their data has been illustrated to show what the plumes would be like. And once again, Europa's ocean is considered to be one of the most promising places that could potentially harbor life in the solar system. And then, of course, the third press release from NASA. As I come from Belgium, I do have to mention the work from my colleagues from the University of Liège in Belgium, which is so very, very recent press release. Once again, the habitable zone, once again, most likely to have liquid water, once again, could have liquid water, key to life as we know it. And here just the representation, the Trappist system. As you know, it was called after the Trappist beers, and also the speculoos, which is a typical Belgian biscuit, which is a name that was also being used. So once again, places that are conducive to life. So for NASA, the mantra looking for life in outer space is definitely follow the water. So, but of course, I think we will all agree that over here, that water is, however, no guarantee for life, whether it's little green men or microbes. So whether we're looking now to what the discoveries that have been made for the fossils, it doesn't mean that there's water, that we're necessarily going to have any form of life in that consideration. So there is absolutely no guarantee that a watery celestial body will automatically play host to life. But it still remains what is being used, the terms being used, which is implicitly water remains associated to the notion of life, but not only water. As a chemist, also have to mention that organic is also often associated to life. And to give you two other examples of texts that we can see coming from a space life science lecture, which dates now a little bit, but it is from the talk that was given. Radio astronomers have discovered a vast array of organic molecules in the interstellar medium. And what is the conclusion that they automatically want to come to? Life must be commonplace in the cosmos. So water, life, organic molecules also leading to life. And over here from a more recent post, complex organic compounds. So this was a post that was put regarding a very serious article in Nature where they had just described the molecules they'd found, making no hypothesis whatsoever leading it to any form of life, but taken over by somebody on their blog, and it comes complex organic compounds, once again leading to the fact even when life is not present, as if it was a surprise to have organic molecules and not to have life associated. So from that, what I wanted to say is that we have to be extremely careful of these simplifications, even regarding water. And I think many of my colleagues who are going to talk after me will probably be showing similar forms of data. Because if we look at the abundance of the elements in our galaxy, taking silicium as one, what do we see? That hydrogen, organic point of view, that hydrogen, oxygen, carbon, and nitrogen are extremely abundant. So if the atoms are extremely abundant, why would the molecules not also be abundant in the universe? So water and organic molecules of an abiotic provenance must necessarily also be abundant in the universe. So there's no reason to make this simplification. And to highlight, so this is just the type of example of organic molecules detected in space of completely abiotic origin. So these molecules are of interest because they could be precursor molecules for the molecules of life as we know it today. But this is this very complex organic molecule that was being detected by the team in Hong Kong, and that physics world was astonished to find that it was found in the interstellar space without there being any form of life out there. So this is the cartoon that I'm going to be showing to show you this simplification and the way journalists usually take it. So over here you have the spokesman from NASA. You probably can't read, it's a bit too far away. We have some circumstantial evidence that might point to a tentative way, to the slight possibility that maybe 3 billion years ago there was a chance that there could have been life on Mars. And here you have the journalist. Did you hear that? Life on Mars, the universe is inhabited, a new era dawns, with the caption below, let's hope life on Mars is more intelligent than life on Earth. So this is just the way scientists could be just having data, but the way the press takes it over, it's much more interesting to represent it this way rather than to present it in a critical manner. So all this so this is just the mural at the NASA Ames Research Center, just showing the tree of life, the evolution, if you want, and different interpretations for bringing water, which I will not go into any detail on Earth. But the question that we should be asked, and that I can ask as a chemist, is why is water considered a key element for life? Why is water considered to be essential for the emergence of life? Or in other questions, to really put it back as a physical organic chemist point of view, is it possible to achieve a high level of organization at the molecular or supramolecular level that is able to lead to groups of molecules, a certain form of organization that could be at the origin of the chemical evolution leading to biological evolution? But would that be possible in a solvent other than water? So that basically is the question I'm asking today, and the rest of my talk is going to be to try and answer that question with you. So the outline, and this is where we can have a little bit of a debate, is life. Do we need a definition? We can tell me what you think about that. Then I'm going to talk about water, the molecule, the solvent, water, the biomolecule, and then to finish by answering the question, liquid water, is it essential for the emergence of life or for any form of life in that matter of fact? So I don't know if anybody else is going to debate the question, or it's a question I can debate with you, is do we need a definition for life? Yes, no. And yes, why? Would we need one? No, why not? So do we need a definition was my question. And I think my answer is going to be, and I'm going to illustrate, is we don't need a definition. But we might like one, but doesn't mean we need one to be able to do the work. And it's going to continue a debate we had at lunchtime around our table about when do we need a definition or not. And this is coming back to the fact that if you're looking at the emergence of life, to go from non-living to living, at some stage you must have been not fully non-living and not fully living yet. So there must have been some form of transition. So basically, it's where do you put the cutoff? Where do you decide that's not living and I'm living, I hope. But it has to have been progressive. And at the same, so you'd had not yet fully living and not yet living. So basically, it's one between the two. And like we said, it's a debated question today. Viruses and spores, it's already there. But we're not the ones. Aristotle already knew it. He said, nature proceeds little by little from things lifeless to animal life in such a way that it is impossible to determine the exact line of demarcation, nor on which side thereof an intermediate form should lie. We think about evolution, and we had to have chemical evolution before. When was your chemical system considered something which was living and not just an ensemble of chemical molecules? The same way, to make an analogy with Charles Darwin, with the notion of species, if you're evolving from a species Y to a species X, at some stage you are not anymore fully Y and not yet fully X. And Charles Darwin said it himself. He looked at the term species as one arbitrarily given for the sake of convenience to set individuals closely resembling each other. So once again there, it's not very clear. And I think the idea that we want to have a definition for living or not living is we desperately as human beings want to put things in boxes. We want to be able to say it's one box or it's another box, and that box in the middle, we're not very comfortable with it. And this is coming from blog I was looking at about life and non-life are artificial categories, that it's a human tendency to want to put things in categories, but we should be thinking in things in terms of a continuum. But defining life as a category, as something in a box, and whatever is outside the box is non-life, will continue to produce exceptions. So I think it's no longer what the type of logic you should be using. It's not category life and category non-life. The type of logic we should need is fuzzy logic, where you're going progressively from 0 is non-life, 1 is life, and somewhere in between, a molecule which is a molecule of life, you could already consider that with a non-zero index. Amino acids I put in 0 because we know we can create amino acids abiotically, the Urey-Miller experiment. DNA has to be something which is non-zero because up to now we have no hypothesis, no model to explain how I would have been able to have DNA in an abiotic way. So that is already a signature of life, so it's not 0, but a molecule of DNA. I think everybody's going to agree we're not going to consider that being alive on its own. So this is more behind it of fuzzy logic. Now, do we need a definition? Somebody said, so we know what we're working with, and this is the thing is that there's no natural criteria for non-living and living. And talking about time, which was the big question of debate today at lunchtime, is that physicists do extremely precise work and have no problem being quantitatively perfect, being qualitatively exceptional without having a definition for time or having a definition for energy. So it might help. You need to have something which we agree on, but you don't necessarily need to have a very precise definition to be able to do exceptionally good work. So I think the work that can be done for people looking for in the field of exobiology or in the field of biology, in the field of artificial intelligence, in the field of artificial life, you can do exceptionally good work without necessarily all agreeing on a definition of what is alive or not alive. Now, I do need somehow to be able to continue my talk, to be able to say why water is important. So I have to decide at least the minimum criteria. So now the idea is, what are the minimum criteria you could imagine? Basically, the idea, trying to get to, we do need some sort of a system. We need an environment. We need to be confining, because if we're found there with all these molecules interacting with each other and they're all diluted in the ocean, we're going to have a bit of a problem. We're going to need something which is confined. So the idea of having a form of boundary would be important. But of course, if it has to be out of equilibrium, that boundary also has to be thermodynamically able to exchange. So it has to be, from a thermodynamic point of view, a membrane. We need I didn't say a membrane, I just said something to confine for the moment. We'll decide what it has to be. So it's something that can confine. It has to, of course, be open in the thermodynamic sense of the word. You have to be able to exchange matter, you have to be able to exchange energy. Otherwise, if it's just confined, we're not going to go extremely far. Anything else? Chemists, what do we need in there? Something's going to happen in that environment. We do need some chemistry. We do need some reactions to take place. So basically, I think just the minimum conditions for a chemist, without saying that there might not be other conditions which are there, it's to have an open, and I did mention from a thermodynamic point of view, system with a certain form of integrity, but it also needs to be coded system, in the sense that you are going to be able to have this notion of replication, so that information sort of has to be there to be able to pass on to the next generation. So it's an open and coded system in which spatio-temporally regulated chemical reactions take place, which enable the system to maintain its, its integrity, to regulate its exchanges, and to divide into two systems, not, of course, absolutely identical. Otherwise, if it was just dividing into something which was identical, we wouldn't have any form of evolution. So, putting it differently, trying to put it more in a schematic point of view, basically we need some form of a semi-permeable boundary, which I've represented over here, semi-permeable by the fact that you can have exchanges between the in and the out. You need to have some chemistry occurring inside with the possibility of transmission of information. And also, we do need it to take place in a solvent if we want to have a system where reactions can take place. If we find in the gas phase, you're going to be found in such a huge volume, the probability of contact between these molecules to have something which is evolving is going to be extremely low. And if we're working in the solid and the condensed phase, there it's going to be on the kinetic scale, the time scale, where things are going to be so slow. I mean, there is a geological time scale. Over here, we're trying to see things a little bit faster. So if we're considering things in a condensed phase, a solution phase would be the most appropriate. So the whole question over here is going to be linked to this notion of the solvent that we're going to be looking at. So since the title already says it, we're going to be looking at water and why water would be the right solvent to be able to fulfill these different conditions: a boundary, chemical reactions, and the possibility of the transmission of information. So to go back to water, looking a little bit at the physico-chemical considerations about water as a molecule and water as a solvent. And I'm going to take you back to your first year chemistry course as an undergraduate, the electronic configurations of the atoms of water. This is just to remind you that it's 1s1 for the hydrogen, and then the oxygen with its 6 electrons in its valence shell, 1s2, 2s2, and 2p4. But what's extremely important is that, of course, the hybridization of the atomic orbitals of oxygen in water is sp3. Why is it important? Because we end up then with a tetrahedral disposition of the 4 sp3 orbitals, 2 forming a chemical bond with the hydrogen atoms by overlap with the 1s orbital of the hydrogen, and then you're left with 2 sp3 orbitals which both contain a lone pair of electrons. Why is that important? It's important because the water molecule is not a linear molecule. So if you ask children, you say it's H2O, children who have no knowledge whatsoever of the disposition and the hybridization of the atoms would probably draw it HOH as a linear, but it's very important to know it's not a linear molecule. Over here you have, it's 104, approximately 104 degrees over here, valence angle, and you have over here, of course, the two non-bonding electrons which are found. Now, why is that important? Because water, in this sense, is going to be, first of all, a polar molecule, because you have the difference in electronegativity between the oxygen and the hydrogen. So you're going to end up with a resulting dipole moment to your water molecule, which is one of its characteristics, physicochemical characteristics. It has a dipole moment of 1.85 dBi. Now, the molecule as such, it has the possibility of forming what are called hydrogen bonds. So the hydrogen bonds, I think for chemists that should not be a problem. For biologists it shouldn't be either. Others have, somebody never heard of the hydrogen bonds? I doubt it. I think it must be part of most curricula. So the hydrogen bond is characterized as the sharing, if you want, of the electronic density between a hydrogen which is has a covalent bond with an electronegative atom, so will definitely be polarized delta plus, where there's going to be an interaction with the non-bonding electrons of another electronegative atom. If we're looking at atoms which are commonly present in organic molecules, would be a nitrogen or would be an oxygen. And it is known, and the biochemists love the hydrogen bond, because if you're looking at the three-dimensional structure of proteins or the three-dimensional structure of DNA, you see that the distance between the hydrogen over here is longer than what's expected over here and shorter than what's expected there. It's really this electronic density which is being linked, which is of course giving rise to what's called a non-covalent interaction, giving a certain form of cohesion between the different molecules. So in the case of water, where we've got the two hydrogens which are delta plus, and at the same time we have the two pairs of non-bonding electrons, theoretically, a molecule of water should be able to form 4 hydrogen bonds, twice a hydrogen bond donor and twice a hydrogen bond acceptor. So you would have, in this case, a sort of a tetrahedral configuration, a water molecule inside of the tetrahedron, the pyramid over here, and then you would have water molecules at the summits of your pyramid. Shown over here, so this is the oxygen and the hydrogens. You're seeing over here, once again, with the dashed lines representing the hydrogen bonds between the water molecules. And theoretical chemists who are interested in the modeling, the structure of water, are really confronted to a problem. There's no model, there's no fully accepted model for the structure of water, and there's certainly no model which is able to explain water from the solid phase all the way through to the gas phase, so no theoretical model. The consensus now, or there's an idea now that actually liquid water, if you're looking at liquid water, you would have 2 subsystems in there. You'd have clusters of water where there are molecules with a tetrahedral coordination. These would be called the low density clusters, so really forming this nice like crystalline structure of every water molecule having its 4 neighbors, surrounded by a high density where it's disorganized molecules. And the example which is often given is like if you're going to a nightclub and you're on the people who are sitting outside in very organized, structured way around the tables drinking, and the people who are on the dance floor who are in more motion and they're active, but people are going in and out. So you're going between sitting down to going to the dance floor. So they've called it the molecular dance of water. These clusters, of course, are extremely, extremely short-lived. 10 to the minus 11 seconds. So for those of you who are old enough to remember the huge debate about the memory of water, water has a memory, but it's very, very short. Suffering from extreme Alzheimer, so 10 minus 11 seconds, any form of structure which is there. And in this model of these 2 subsystems, of course, if you're increasing the temperature, you're going to decrease the number of these more low density clusters to have a higher number of disorganized molecules. So
naively expect the coordinated molecules to be in a higher density?
No, because over here they're going to be able to dispose themselves so that they have their hydrogen bonds, and the strongest hydrogen bonds are when they're actually in a linear configuration. So you would want to have, this is not going to represent necessarily the most structured one, bad example, but you'd want to have these three atoms in a linear configuration and not in an angle. So if you want to have the most highly coordinated way, it's going to be lower density, while you're able to bring them much closer together. If you're having the two hydrogens which are coming close to each other, you're able to have something which is more dense. So this is the 3D network of molecules, which is of course at the origin of water as we know it. The water that's there, it is a condensed phase. So it is, as a chemist, and as chemists work in the field of supramolecular chemistry, we can just say that water is just a gigantic supramolecule. You just have all these molecules which are interacting with each other via these non-covalent interactions. And it can also be an example of what we can call emergence in chemistry, is that the sum of the parts is better than the parts taken individually, because liquid water is not the same as just having an ensemble of molecules which are there. It has properties which are characteristic of the solvent, which are not just a characteristic of the molecule taken on its own. So now to look at certain characteristics of physico-chemical characteristics of liquid water, and I'm going to compare certain characteristics, not all, and I'm going to compare them to other solvents. And the choice of solvents I've made is because these solvents are sometimes shown or discussed in the literature as being possible solvents for where life could take place, where life could occur, or where there could have been the emergence of life. So first, looking at the superficial tension of water, taken at 25 degrees, it's extremely high. A solvent which starts coming to the same value is formamide. If we look at its specific heat, it is also much higher than the solvents that we know. So the specific heat is the fact that the amount of the temperature has to be able to increase the volume of water by 1 degree, the amount of energy you would have to provide. So that's the specific heat. The superficial tension. Dielectric constant is also extremely high. Formamide is higher, but here we have a dielectric constant of 80. So what are the illustrations here? The high superficial tension is the high cohesion of liquid water. So the fact that drops of water are going to be circular when you've got your drop of water hanging, or when you have these insects which can walk on water. The very high specific heat of water means that water is a very good thermal buffer. If the outside temperature is changing quite drastically, the temperature in the water is not following the outside temperature, whether it's going up or whether it's going down. So it has sort of question of being able to have a certain constance of the temperature. And the high dielectric constant means, of course, that you're going to be able in water to shield electrostatic interactions. Reason why, if you're putting salt in water, you're going to have Na plus and Cl minus, with, of course, if you're looking at Coulomb's law, the dielectric constant comes at the denominator, so you're going to be screening this interaction. That would not be like if you were in chloroform. NaCl just sticks as NaCl, and also doesn't even dissolve. It sinks straight away to the bottom of your flask. Another physical-chemical property of liquid water is that ice floats on water. And over here, before saying what this has as a consequence, possible consequence that we're interested in, this is just to show you the phase diagram and to also explain why theoretical chemists or theoretical physicists have such a hard time trying to find a model to explain water. Is that if you look just in the solid phase, there are 15 known crystalline phases for ice, which you obtain if you're changing the temperature or if you're changing the pressure. So certainly if we're going from liquid water, we're going to be going at the normal temperatures, you're going to have a specific phase that we're going to have, but otherwise it's not that easy. The crystalline form is not just unique. You have these different morphs of ice. Now, the fact that ice floats on water has as a consequence that you're going to be able to protect, if we're looking at life today, protect life underneath. So if you're going to go to the cold Arctic or Antarctic oceans, you're going to have the ice formed on top. It means the fish are still downstairs, below rather, being able to swim around in the cold water. So you're not going to have, like other solids, where you're going to go to the bottom and then it's going to keep the water on top. It's going to be becoming colder and colder. There's also, if you want, a certain form of buffering which is offered by the fact that the ice is on top of the liquid water. So all this 3D network of water molecules is at the origin of these abnormal properties. So they especially can be considered as abnormal considering the small size of the water molecule. It's H2O, 3 atoms, 18 molecular weight. If you're comparing to other more complex molecules, where you could consider other properties coming from the fact that they have a larger volume, a larger surface area. But water in that case is extremely abnormal. It's high boiling temperature, for example, 100 degrees compared to methanol, which is 50-something degrees, or if you're looking at methane, which is the same molecular weight, which is going to be gaseous until minus 50 degrees. So that really is due to its 3D network. And over here, this is the example, the insect walking on water, and the drops of water here for the high cohesion of water just is there. Now, so this is water as its solvent. Now we'd like to be able to see what's possible to do in water. So what I'd like to look at now is the possibility of water as a solvent. So being able to solubilize different types of compounds. Now, as far as ions are concerned in liquid water, if you're putting cations or if you're dissolving anions, and here as an example I've taken the sodium cation or the chloride anion, but it could be sulfate, it could be potassium, it could be hydrogen, proton if you want, as a form of H3O+. Water will solvate both cations and anions. In the case of anions, as you will see over here, so these are my little water molecules, represented a little bit as Mickey Mouse. Over here, you're going to have the 2 hydrogen atoms which can form hydrogen bonds, if you want, with the electronic density of the chloride. And in the same way over here, we'd have the delta minus of the oxygen, which is going to orient itself towards the sodium, in this case, cation. So in both cases, cations like anions can be solvated by water molecules. The water molecules can accommodate the cations and the anions, and you can solubilize them to a certain extent. If now we want to look at the solubility of polar molecules, I've just taken an example here. The example over here is glucose. As you know, so glucose is not your table sugar, but it's one of the components. But you can find glucose syrup. You can put a lot of glucose in water, so it's soluble. It has a high solubility. And in the case of glucose, it of course is a molecule which has some parts which are the carbon atoms over here are not necessarily going to be what wants to be in water, but it's going to be a balance over here. So this is the glucose molecule shown more in a space fill representation. The carbons and the oxygens are in red, and over here in white you're going to find the hydrogens. And if you're in that situation, once again you're able to form a whole series of hydrogen bonds. The oxygen can be a hydrogen bond donor, and the hydrogens on the hydroxy group in glucose can be hydrogen bond givers. So in this case, the glucose molecule can once again accommodate, it's a good solvent for polar molecules, water, polar molecules, ions as well. Now the question is, what about apolar molecules? What's going to happen if you have a molecule which is not considered to normally be soluble in water? So this is where my 10 minutes of thermodynamics is going to come in, and I'm going to look at an example to show you that of course the solubility in water is going to be a balance between these intermolecular forces between the entity you're looking at and the water molecules. And if you're looking at these intermolecular forces, you also have to consider any entropy changes. So it's enthalpy and entropy which have to be taken into consideration. And the example I want to work with is a very, very simple molecule. It's a molecule, or an atom rather, that we've extensively studied in my lab in Brussels. It's the xenon atom. So it's an atom. And nobody's going to debate about the fact that it's an apolar entity. It's got 54 electrons, but it's an absolutely spherical entity. It doesn't have a dipolar moment, doesn't have a quadrupolar moment, doesn't have an octupolar moment. On its own, it's a nice spherical entity. And you can solubilize xenon, not a lot, but you can put to something like 5 millimolar of xenon in water. So if you're able to put the xenon in water, it means water must be able to accommodate it. And the fact that it has this 3-dimensional network of hydrogen bonds is able to accommodate it. And in this case, what's going to happen is you're going to have, a little bit like in the clusters I talked about earlier on, you're going to have the water molecules around the xenon, which are going to structure themselves even more than what you have in the bulk. Why? Because if you are able to form 4 hydrogen bonds, in reality, in this molecular dance of water, on average they're forming probably 3 hydrogen bonds. So if these water molecules structure themselves extensively around the xenon atom, you're going to be, so these are the water molecules represented, only the oxygen atoms, not the hydrogens. They're going to form what's called an iceberg model. It's going to form really like a clathrate. It's going to structure itself strongly around the xenon atom. And so this iceberg model, and this is what's called hydrophobic hydration. So that's why you're able to put these small molecules, this network will accommodate them by creating a hole, but to create that hole, since it's probably losing hydrogen bonds to the dancing molecules, it's really getting stuck. It's sitting on that chair and it's got its bottle of vodka in front and it's not going to be moving from where it is. Xenon vodka, I don't see. Doesn't. But of course, this comes at a cost. So if it's forming these, let's start from the bottom, it's got this interaction enthalpy is favorable. It's forming these very strong hydrogen bonds. It's also orienting itself so that it forms good van der Waals interactions with the xenon atom. So favorable dispersive interaction, these London interaction. So the delta H of dissolution is favorable. It really it doesn't bother it. But entropy-wise, you're structuring these water molecules. Of course, it's not in favor of trying to dissolve these molecules which are present. So if we have to look at this entropy-enthalpy balance, the entropy is not favorable. The delta S of dissolution is negative, but the interaction enthalpy in this case is also negative, so it's something which is favorable. So if we consider both of them now, this hydrophobic hydration, a favorable enthalpy and a high loss of entropy, over here it doesn't really compensate the loss of entropy, reason why you can only dissolve a little bit. It's like methane gas. You can also dissolve methane gas in water, 3-4 millimolar, but not much higher. Why not much higher? Because of course the loss of entropy is costing more than what you're gaining from the favorable enthalpy over here for your dissolution. But it's a balance between the two, and xenon is actually quite soluble compared to methane because in this case the enthalpy is extremely favorable with the xenon atom as well. Is that all right for thermodynamics? A little bit more coming up now, because from that I want to introduce the notion of the hydrophobic effect, because something which is a characteristic of water which is very marked, because not many other solvents have what are called a solvophobic effect. So hydrophobic effect just means the result of not liking water. What would be the consequences of not liking water? But to be able to give you a definition of the hydrophobic effects, what I'd like to do is to look at the associations of molecules, so the reason why A plus B will form an AB complex, and to compare that associations of molecules in the gas phase to the associations of molecules in water, and to be able to see what is the characteristic of water in that case. I could have done it, but it just lengthens my talk and it's not necessary. I could have shown you as well what's happening if I'm doing the associations of molecules in an organic, non-structured solvent. So let's first look in the gas phase, represented here a little bit by a Pac-Man symbolism. If I have a molecule A over here and a molecule B, which can form in equilibrium to form a complex, which is a complex AB, I can represent over here what's called an affinity constant. The ratio, if I'm working in solution and I have low concentrations, I'm going to express it as an organic chemist, representing it as the concentration of the complex AB divided by the product of the concentration A and B. If I'm working in high concentrations, I would be using affinity terms and not concentrations, but over here, or activity terms, sorry, rather than concentrations. And over here, you have your affinity constants from which you can have your delta G0, so the standard free energy. and it's going to be minus RT, the logarithm of this affinity constant. Now this delta G0, the standard free energy change, is going to be characterized by a standard, the change in the standard enthalpy, and minus T, the change in the standard entropy. And in this case, if you're working in the gas phase, A is out there all alone, B is out there all alone, and they meet each other, there is no doubt that 1 plus 1 giving 1 is not favorable as far as entropy is concerned. So this is always going to be negative and is always going to be unfavorable term in this association. So entropy-wise, it's not favorable to associate in the gas phase. So if there is association occurring in the gas phase, it has to be enthalpy driven. There must be interactions. When A and B are together, you must have over here favorable interactions which can occur, hydrogen bonds, favorable electrostatic interactions, favorable London dispersion interactions. You need cation pi interactions, pi, however you want to call them, you need these favorable intermolecular interactions. So delta H0 will always be negative, will always be favorable if you're looking at the association in the gas phase. Now, if we look at what's happening in the liquid phase, and especially if we're looking at what's happening in water. Represented over here, I've represented two amphiphilic molecules, molecule A and molecule B, there, because they're in water, so they at least have to be soluble to a certain extent. And on these two surfaces over here, where I've drawn my little water molecules, these are the hydrophobic surfaces where we have these structured water molecules. The ones I explained to you, the ones forming the cage around the xenon atom. So the ones that really locate themselves to try and form the good hydrogen bonds between themselves. So these are these structured water molecules on the hydrophobic surfaces. If my molecule A and my molecule B associate and they form my AB complex, the contact area over here will be able to free the water molecules. I will have what I've called over here the liberated water molecules, the ones which are freed. So in this case, if I look at just the entropy of the system, I have over here A 1 plus 1 giving 1. So as far as A and B are concerned, definitely there is a loss in entropy. But in this case, I must consider that it's A plus M molecules of water, B plus N molecules of water, and a certain amount of molecules of water over here have been freed. So in this case, if the entropy of A and B are decreasing, what is certainly increasing is the entropy of the water molecules. So over here, the A and B decrease in entropy, but the water molecules, we have this increase in entropy. So there's this huge entropy gain when you're in water with these amphiphilic molecules. So as far in this case of A plus B giving the complex, the entropy over here will always be positive. In the gas phase, it was always negative. Over here, when you're associating in water, you will always have these water molecules on the surface which will be freed, so you will be entropically favorable situation, while as far as the enthalpy is concerned, positive, negative will really depend on the type of complex you're forming. But in all, over here, you're going to have this association between A and B in water, which is going to be entropy driven. So it's not the enthalpy which is guiding it, it's the entropy which is guiding it. And this is what we call the hydrophobic effects. So it's not an interaction, it's the result of being able to have the expulsion of these structured water molecules which will gain in degrees of freedom to be able to have a delta G0 which is going to be negative, which is going to be favorable for the association complex. So delta S0 is positive, and as far as delta H0, it really depends one system or another system. So that's the hydrophobic effect. So this is it. It's the case of what's formed micelles. It's also what you find when you've got these micellar solutions for removing makeup or for creams which are present. It's exactly that. You have amphiphilic molecules, a long hydrophobic chain and a polar head. When you put them in water, the chains do not want to be in water, and you will be forming, this is my representation of a micelle, where you're going to have the hydrophilic heads on the outside, the hydrophobic inside. And what's going to happen when you're using soap has got these amphiphilic molecules, and then the dirt you have, the grease you have on your hands or on your body or elsewhere, is going to be able to dissolve over here inside the heart of these micelles, and then you wash everything away. So this is the association of hydrophobic molecules to form. An example is micelles. I'll come to other examples. So that's water as the solvent. So we saw that it had certain characteristics. The fact that it can solubilize anions, cations, small molecules. It can even solubilize small hydrophobic molecules. But we've also seen that associations in water are going to be entropy driven, that you have this hydrophobic effect, which is a term which you're going to take into consideration in water, which you don't have in organic solvents, because organic solvents are not structured. So whether organic molecules are around the surface or outside, there is no change in entropy, so you won't have this entropy gain associated to any form of association. Now going more now to the biology side, as far as biology is concerned, over here is now the importance of water in biology. I will not go into much detail. What I want to talk about is what I've called water the biomolecule. It's the importance that the molecule of water plays for the biomolecules that we're interested in today in life. So it's important, water is extremely important for the structure and the stability of proteins, so big macromolecules. It's also important for the structure and stability of nucleic acids, and it's also extremely important in any form of molecular recognition processes which are involving these proteins, these nucleic acids, or also smaller molecules. So proteins. So a protein is a polymer, all these amino acids, one next to each other. So it's a polymer of what are called alpha amino acids. 20 different amino acids in all the proteins that make up all the living organisms on Earth today, but it's without even going into that form of detail. It's a polymer of alpha amino acids. And then when we talk about the structure of proteins, we'll talk about a primary, a secondary, a tertiary, also for certain systems a quaternary structure. It's not a question of importance, it's just a question of being able to put categories in there. The primary structure is just the sequence of amino acids, so basically the beads that you have on your necklace, just which beads are following which beads. You've got 20 different colors, just the way they've put one behind each other. That's what we call the primary sequence, the primary structure, excuse me. The secondary structure are just elements of regular structure which are found in most proteins. And what's drawn over here from the figure I have, the most common are what's called the alpha helix. It's just the fact that you will find amino acids forming an alpha helical structure where you have a specific number of hydrogen amino acids following each other, and it's certain distance between these different amino acids. That's the alpha helix. And another element of regular structure which is found are what are called pleated sheets, beta pleated sheets, parallel, anti-parallel. There is some sort of variety in there. So these are the two elements, regular elements of secondary structure. So these are the ones that we found. So it's as if you're finding in a house windows and doors. So these are the categories, those are the elements of secondary structure. And then what's called the tertiary structure is really the way that all these elements of secondary structure are going to dispose themselves relative to each other, and the bits of random coil which are going to be able to link them all together. Quaternary structure is when we have two proteins which form, or 2, 3, or 4 proteins which form the actual active unit. An example being hemoglobin. There are 4 different subunits in hemoglobin, 4 different polypeptide units, and that's what we're going to call the quaternary structure. Now proteins, whether they're enzymes, whether they're receptors, or whether they're structural proteins, the ones we have and all living organisms have, they adopt, I did put in general, one preferred 3-dimensional structure. There's of course now all these prion-based diseases, of which Alzheimer's is linked to, and it's that same category, is where proteins can adopt sometimes two different structures. But generally, to be able to do their role, to be able to function, to be able to fulfill what's required of them, they adopt a 3D structure. And that 3D structure needs to have some stability while still being able to give some form of flexibility. It's what was initially by Fisher elaborated as being the lock and key principle. You need the lock to have a certain shape for the key to fit in. Now things have evolved. It's not a lock like we know over here, which is in metal and you can't have any flexibility. There is flexibility which is required as well. So, considering now this three-dimensional structure of proteins and their possibility of having some form of flexibility, where does water play a role? First of all, the hydrophobic effects. Although it's still a much debated question as to how do proteins fold in vivo, even in vitro as well, it is considered to be the driving force, the hydrophobic effect of protein folding. In the sense that if you have your protein, your long sequence of amino acids, and you have your different side chains, the ones which are hydrophobic, the initial step will be all these hydrophobic side chains will come together in the core of the protein, will form that first core, and that's going to be driven by the hydrophobic effect, the water molecules which will be liberated, which are going to hide these sides from the water molecule. So the burial of these hydrophobic residues in the heart of the protein. So this will occur in water because of the hydrophobic effect. You take the same protein and you put it into an organic solvent, even if you put it into ethanol or into methanol. First has to be soluble. It will not go and fold into a well-defined three-dimensional structure. So hydrophobic effect, but it's not the only reason why water is important for proteins. They're also an integral part of the 3D structure. And the best for me to do is to show you the result of some X-ray structures which I've taken out of the protein data bank. If you're looking in this glucoamylase protein from some microorganism, it's observed when you're taking the crystal structures of this protein, whichever crystal structure you take, you recrystallize the protein, you reanalyze the structures, you see that you have all these water molecules which are very nicely positioned within the protein. Two reasons. One, it's a very small molecule. 2 hydrogen bond donors, 2 hydrogen bond acceptors. So if the protein in its core wants to form certain ties, water molecules can be a bit the sticky tape between the two, forming a hydrogen bond here and forming another hydrogen bond over there. So it's able to be a linker molecule which is present. And in the case of this system, this chain of water molecules, it's also a way of transferring protons. So it's going to come from H3O+, the proton's going to go here, 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 here. So it is a channel for H+, for protons to be able to go and travel to the core of the protein which is present. So it's an integral part, playing this role as a functional role and a structural role. Same case over here for the water molecule which is bound over here to 3 different amino acids by hydrogen bonds in a ribonuclease, T1 found from one species, but it's conserved in family of ribonucleases from families of different species. So in this case, the water molecule is creating the linkage once again of these different parts. So water and proteins are important not only because of the hydrophobic effect, but also because water as such is going to be able to be part of that molecule and keep that structure as a 3D structure which has a certain form of stability, while at the same time being able to give it some flexibility, because these water molecules, they will be exchanging. They have a lifetime in there longer than the 10⁻11 seconds, but they do exchange with water molecules which are outside in the bulk. There is some flexibility. It's sort of a sticky tape. It's more like a post-it. It can come off and go back on. It's not a high quality scotch which has been put over there. So hydrophobic effect part of the 3D structure. And then of course, but this is then starting to go into enzymology and seeing that water, of course, is used as a reagent. The small molecule is a co-substrate, if you want, of your proteins. Many hydrolysis reactions, for example, will be requiring the presence of a water molecule in the active site. So that's for proteins, and we can go through a similar type of scenario considering the role of water with nucleic acids. So in the case of nucleic acids, so these are polymers of nucleotides. These nucleotides, each nucleotide is formed by a sugar. In the case of DNA, it's deoxyribose. In the case of RNA, it's ribose. On this deoxyribose, in this case, you have a base, CTGC, one of the 4 bases, puric bases or pyrimidic bases, which can be found. And then you're going to have one sugar linked to another sugar by a phosphodiester bond. So you have these phosphate groups. So a phosphate group, a sugar, and a base, a phosphate group, a sugar, and a base. This is going to be the linear sequence of your nucleic acid, these different nucleotides, 4 possible bases in DNA, 4 possible bases in RNA, 3 are in common. And in the case of DNA, as you probably all know, even if you've never done any biology, the double helix of the DNA, we hear enough about it. So it's a double helical structure, 2 anti-parallel strands, which are going to form a right-handed helix. You're going to have base pairing inside between the bases by hydrogen bonds, 3 or 2 hydrogen bonds, depending on the pair you're looking at. And on the outside, you've got the phosphate sugar backbone on the outside of the double-stranded DNA, represented here in its bDNA form with a narrow and a wide groove. In the case of RNA, it's a single-stranded structure, and it just folds back on itself and can adopt double helical regions, but also other forms of structures which are there. So without going into different forms of RNA, the tRNA or the ribosomal RNA, but we do have systems which are once again polymers, which once again adopt a well-defined 3-dimensional structure, which of course must also have some dynamics in it. Otherwise, how would you be able to do DNA replication if the double helix didn't unwind? How would you be able to have the transcription from DNA to RNA if there wasn't base pair opening? So you do have this breathing of your molecules which are present over there. So where does water play a role with these nucleic acids? Phosphate groups on the outside. There's a phosphate group for each nucleotide. So basically, if you're looking at your DNA double helix, the outside is heavily negatively charged. And if you have all these negative charges next to each other, they just want to explode. They're just, Coulomb repulsion is going to take place over there with all these phosphate groups. But what happens with these phosphate groups? It's true that forming this helical structure tries to get them further away from each other, these phosphate groups. But it's also going to be the fact that you have hydration sites, that on these phosphate groups, the water molecules can come and form hydrogen bonds. And this is going to help screen the electrostatic repulsion between 2 phosphate groups which are next to each other. So it's also going to decrease, so it decreases this electrostatic repulsion. You also have the base pairs and the sugars, which are inside. You can still, with those 2 grooves that I mentioned, you do have water molecules which can go into those grooves and form hydrogen bonds with the sugars, which have OH groups. Remember the glucose molecule I showed you in the beginning? You're able to form in that position hydrogen bonds, which are also going to contribute to stabilize this 3-dimensional structure of your nucleic acids. So in this case as well, the water molecules condition and stabilize the 3D structure of nucleic acids. So we see that water is important for the structure and the stability and the dynamics of proteins, and for the structure, the stability and the dynamics of nucleic acids. So these 2 polymers which are important for life as we know it today. Now to come back to my little Pac-Man model, water is also going to be extremely important in molecular recognition. Because if you want to have a transmission of information, if you want a chemistry to be able to take place, A must interact with B. If A just stays A's and floats around and has no interaction with B, not much is going to happen. Everybody's just leading their own life, if we want to give it a life, and nothing's going to be happening in that case. So if we go back here, we're going to take what I called a receptor molecule with a ligand. The receptor could be a protein, could be DNA, could be any other type of entity you might want to put over here, a carbohydrate if you want to call it that. The receptor, you have your ligand over here, and you form your association complex with, in this case, the you would want, of course, if you're looking, this is exactly the same equations I showed you earlier on, you will want to, of course, if you're having a certain form of interactions taking place, you want binding to occur, but over here just you also want some form of selectivity, because otherwise you won't be able to have things which are being specific, going towards a specific direction. We don't even have to go into that form of detail. It was just to add, of course, the information that as far as the chemistry of molecular recognition taking place in biological processes, there's binding, but there's also selectivity, which often comes from the complementarity in shape and intermolecular interactions. So the stability of this complex that you form is, of course, going to be the result of a subtle balance between many non-covalent interactions. So if you can form hydrogen bonds, that's going to be favorable. If you're putting a negative charge next to another negative charge, that won't be favorable, but could be compensated by the fact that you have two dipoles correctly oriented, which are just next to each other, which will compensate for this negative effect. But over here, it is definitely this balance of all these non-covalent interactions are going to be extremely important. But the lock and key model that I just mentioned, the key going into the lock, you can open the door and your event can take place, is not sufficient. And in this case as well, water plays an extremely important role. So you don't only have to look at the receptor and its substrate, but you also have to see how water plays a role here. And I'll illustrate it once again with a cartoon on the next slide. But it's going to be, first of all, the hydrophobic effects, because you want them to come together. And once they're there, they can form their favorable interactions, but you want them to be able to form something which is stable, and the hydrophobic effect is that driving force to bring them together. And then you also have water, which plays an extremely important role at the interface. And this is shown by my very, very basic cartoon. If I'm taking here my ligand, which is red, and my receptor over here, which is green, this is what I've represented as being this hydrophobic surfaces. So the hydrophobic effect, the parts which want to stick together because neither of them want to like water. But this is not sufficient. What you also have, you've got these linker molecules of water. So these small molecules of water, because they're small, which can once again form hydrogen bonds on both sides of the system to link them together. So over here you have, of course, a huge entropy loss, but you've got the enthalpy gain which comes in, while over here you had the huge entropy gain from getting rid of the water molecules. So when you have this association in water, it's going to be the presence of that solvent is extremely important. It has been shown from different studies which are undertaken with receptors and substrates, where you can do some genetic engineering and modifying them to be able to see the role played by water in these different processes. But it is an entropy balance which has to be considered. And to show that and to please more the biologists over here, it's just to show you from studies which are undertaken, so thermodynamic studies using isothermal titration calorimetry. You can look over here without being interested in what they actually do, the interaction between the dopamine receptor and sperinone, which is a substrate of this receptor or a guest of this receptor. If we look at the delta G0, so the enthalpy, the standard free energy of interaction, it's very negative. It's very favorable. So you'll have an affinity constant 10 to the power of 5, 10 to the power of 6 or 7. It's a very favorable interaction. But if you break that down now to the enthalpy and to the entropy, The delta H0 is positive, so not favorable. On the other hand, you've got a very favorable entropic term. So balance of entropy and enthalpy means you have something which is favor, but over here you can see that it is an entropy term and not the enthalpy which is driving this association. And if it's the entropy, water has played an important role over there. The same for the interaction of DNA with RNA polymerase, so it's the transcription from DNA to RNA, the enzyme which is involved over there. The affinity association constants of 10 to the power of 11, so basically it's like it's gluing together if you want. And in this case, once again, what do we have? The enthalpy is not favorable, but there is an extremely favorable, once again, entropy term which is present over there. And then I'm realizing over here there is a bit of an error in my numbers because 229, oh no, it is right, 229 minus 294, you have your 65. These interactions over here are in both cases entropy driven, and in entropy, if there's such a huge entropy term, it is really linked to the hydrophobic effects. And considering the role of water in biology, there is a paper which Philip Ball, which was a former editor of Nature and a chemist, wrote a few years ago in an article which he called Water as a Biomolecule, where he clearly stated over here that water is not a passive solvent in biology but plays an active role in many biomolecular and cell processes. It can be regarded as a kind of biomolecule in its own right, adapting its structure and dynamics to the biological macromolecule, whether it's DNA or proteins, and other cell solute that it accommodates. In particular, water may hold the key to the way some proteins interact, fold and bind their substrate. So water is a biomolecule in its own right. It has to be there. The system would not be active, would not be efficient if it were not present in water. The last section now is, which we can debate about once again, about the definitions we need or don't need, is if liquid water is essential for the emergence of life. So from what's been said, is it really something that we need? Whether it's the emergence of life, or we could say / is it important for any other form of life out there or somewhere far away in the universe. So let's come back now to the minimum conditions for a chemist. Existence of a semi-permeable boundary, represented here with the in and the out, which I've already placed here in a solvent, the solvent inside, the solvent outside, where you need to have chemical reactions taking place. Something has to happen because if no chemical reaction is there. And you also need the possibility of transmission of information. Okay. So that's what's present over there. I wanted to represent here, somehow got lost. I wanted to show you a zeolite, just to show something for the geologist to see something which was solid material. Sorry, it's not there, but imagine it's there. You can choose your favorite zeolite, your favorite structure which is there, which has pores in it. You need a boundary. So the idea of having a boundary, and different hypotheses have come out there, and people say, well, you just need to have a confined space. So if you need a confined space, the confined space could be a preformed cavity in a solid like a zeolite. You've got that cavity, it's present, it's in there. Or it can be space in a laminar material like clay. You really have these sheets of clay which are present, and you could have your environment which is there. Yes, it's a confined space, but it's rather static. If it's going to be there, it's going to be confined in one area. How are you going to be able to divide if you have to have replication? What's going to be able to replicate? How are you going to have things which are going to be able to go elsewhere? How are you going to be able to have all the material needed to arrive to your cavity in your clay? It becomes a system where you might have an apartment building with each little hole something happening, but you're not going to be able to really go outside of that or replicate apart from staying in your zeolite or in your clay. So could we imagine something else apart from these rather what I call static systems? What could we imagine as being a boundary? The idea, if you're looking at now molecules like amphiphilic molecules, is another idea to have this semi-permeable boundary, another possibility would be what we call vesicles. So these vesicles, it's true, these are bipolar membranes if you want. So over here, instead of like earlier on when we looked at these micelles, the drawing I showed you where you had the polar head and you just had one hydrophobic chain, in the case over here, I've drawn two hydrophobic chains. Why? Because then you have something, if you have one hydrophobic chain, you've got something which is a bit triangular. So if you're putting all these triangles next to each other, it looks like a pie, all these different segments of a pie, which are going to be filling out. If you've got your little cylinders, you're going to be ending up being the possibility of forming what are called vesicles or liposomes. And over here, what you actually have is you've got the polar heads and the chains, and over here a series of polar heads again, and the chains towards the inside, and which can form a closed environment in which you've got solvent inside and you have the solvent outside. So liposomes also extensively used in practical everyday life. Drug delivery purposes, but the drug delivery, so the idea to be able to use, so it's used in the food industry as well. So it's used in the food industry like it's used in the cosmetic industry or in the drug industry. The fact is, if you've got water-soluble molecules, but you want to protect them from the environment, either because they'll be destroyed by light, either because they're very volatile, you imprison them inside your liposomes, and then of course if you're using it for in cosmetic purpose or drug purpose, when you're putting your cream, you're going to break these liposomes, you're going to free your compound. And if you use it in the agrochemical purpose, it's to put aromas in it. When you bite into your food, then the aromas are going to be liberated instead of them just being evaporating, because they're extremely volatile. So this is a possibility of having a semi-permeable boundary. Okay, water doesn't go through, and the way life has evolved, there are all these mechanisms to be able to have water which is able to go through these channels from the outside to the inside, and these transporters which enable this to happen. But when you have this, with the advantage of this compared to cavities in zeolites or cavities or areas between layers, lamellars of clay, is the fact you can have what I've called the soap bubble effect. Once it grows, it grows, it grows, it can divide into two. So if you remember as kids, you're blowing into these soap bubbles, they'll become big and then they'll just break into all small little elements. It's going to be exactly the same thing. So this is a possible, I'm not saying the way it's happened, hypothesis of an easy way of seeing things being able to divide. Now these vesicles, this is something that can form spontaneously in water because of the hydrophobic effect. So in this case, it's an easy thing to imagine where water is important. You put your molecules, you bring them in water, you shake it up, you've got to do it. If you want to control the size, now in the lab we do it a little bit more sophisticated manner because we want vesicles for analytical purpose to be of the same size, but they will form spontaneously in an aqueous environment where they're going to bury their hydrophobic tails in the inside and have the hydrophilic heads on the outside and on the inside of these vesicles, and you have an in and you have an out. So this is something which is possible in water. The second condition I mentioned is that we need chemistry. So if we want to have chemistry, we want to be able to have different solutes which are present. We want different types of molecules which are present. And if you consider water, you have a variety of solutes. Cations, anions, polar molecules, small a polar molecules. So a variety of solutes are soluble in water. So you can imagine a very rich chemistry, a very varied type of compounds which can be present. And it is also, as its physicochemical characteristics that we mentioned right in the beginning, it is able to buffer. It's able to buffer because of it's able to buffer temperature, because of its high specific heat. It's also able to buffer against changes in pressure. To try and compress water is much more difficult than if you're trying to compress an organic solvent. So it really has these buffering possibilities against temperature and against pressure fluctuations. It also has the possibility of the ice being able to form, which is able to buffer temperature as well below. The temperature is going to stay at 0 degrees and it's going to be on top where you're going to be keeping a liquid form below. Now all this is possible in water, this solubilization and these buffering capacities to be able to keep something which can sustain itself for a while. And it's possible in water, and it's because of these physicochemical properties of water that we mentioned earlier on in my presentation. So, boundary works quite nicely in water. The chemistry gives you a very rich chemistry because it is water. Third condition I mentioned was this possibility of the transmission of information. Now, to have transmission of information, you need some form of macromolecules. And I'm not saying it has to be protein, and I'm not saying it has to be DNA, and I'm not saying it has to be RNA, although when we're talking about evolution now, if we really want to go back, you need some form of macromolecule to be able to give this transmission of information. But if you want these macromolecules to be there, they're essential, they need to be chemically stable. So you want them still not to be destroyed because they're in very harsh conditions. You don't want them to be in, like some people have suggested, 18 molar sulfuric acid solutions. You need things, molecules which are able to withstand conditions. But they must also be, and that's extremely important, if you want these macromolecules, whatever they may be, have a role, they must be able to adopt a stable structure and at the same time have flexibility. And from being able to compare with what we know for proteins and for what we know with nucleic acids, which are these macromolecules that are essential for life today, water plays an important role. It plays an important role because of the hydrophobic effect. It plays an important role because of the possibility of these water molecules being at the interface between different parts of the molecules. So, possible in water. If you put it in other solvents, you will not be having the possibility of having a stable structure. You can put proteins in other solvent, they will adopt a structure, but you won't need much for them to adopt a completely different structure. If you want things to evolve, you want things to be able to transmit information in the same way, you'd rather have something which keeps some form of stability. What you also need in the transmission of information, you have to be able to form these association complexes. So if you don't associate, you're not going to be able to transmit that information. It's not all radio waves. It's not all, being able to see if there's life out there. Things have to be able, if you want some chemistry, if you're looking at matter, you do need to have the possibility of forming association complexes. And once again, I think from the examples I've shown you, that water plays an extremely important role in these association complexes, which is a consequence of the hydrophobic effect and also the possibility of water being able to form this linker molecule between different surfaces. What about other solvents? All I've been saying over here, can we look at other solvents? So these are two solvents. So methane, we have had in some of these astrophysicists will know more than me, liquid oceans of methane found on, I don't know which celestial body, where it has been suggested that life could have emerged in Titan, that life could have evolved in liquid methane. If you have liquid methane, not much in there that corresponds to any of the characteristics. As a solvent, okay, first of all, you'd have to be at such extreme temperatures and pressures to be able to have liquid methane and to be able to have systems which survive under these extreme temperature and pressure conditions. And furthermore, all these characteristics are not present in methane. It's definitely not a structured solvent. It's definitely not a solvent which can be able to play a role in helping structure, in helping associations, or having any of those physical chemical characteristics which would be able to sustain a stable form of environments. But if somebody wants to debate that, I'm happy as well to debate that, because it's also been why can't we have a silicium world in a methane ocean? We didn't talk about the facts of silicium. We can talk about that afterwards if you want. So looking at other solvents, formamide, ethanol are always also put forward. And formamide, quite a lot of nice chemistry has been done in formamide, being able to show that formamide can help structures, it can really help structure systems. So groups have shown that you're able to have stable structures which are formed in formamide. So this is a molecule, also the possibility of forming hydrogen bonds here by the two hydrogens on the nitrogen, hydrogen bond acceptor on the nitrogen and also on the oxygen. It also has a high superficial tension, a high dielectric constant, and it can solvate cations and anions. So this is the possibility with formamide. Ethanol also has some of these characteristics, a little bit less accommodating, it's a larger molecule. You've got the CH2 and the CH3. This is a smaller molecule which is present. It has a relatively high superficial tension, a relatively high dielectric constant, and it can also solvate anions and cations. But these two solvents, which are often put forward, has some disadvantages. It definitely does not give a chemistry which is as rich as the chemistry as you can have in water. It cannot solubilize an as diverse type of molecules as you can in water. Also, it is much less versatile at interfaces than water. Water is so small. Over here, if you're taking your formamide, and certainly if you're taking your ethanol, it won't accommodate as easily to be able to create that advantage of what I call the post-it effect, to be able to have things being able to be kept together and play this role at interfaces. And more markedly, what is absolutely important, it has no marked solvophobic effects. So that hydrophobic effect that we can take advantage of, which is so favorable in forming associations and forming interactions and in creating the stability of systems, will not be present if we're looking at ethanol or if we're looking at formamide. So these are the characteristics that they have, but which do not lead them as far. So to finish, the idea that there is no doubt that water is more than a simple solvent. It's played its role over there, as which I didn't talk about because I didn't talk anything about the way it plays a role as a reagent chemistry, but it definitely is a reactant, hydrolysis reactions, for example. It's a proton transporter. I showed you that when I was showing you the chain of water molecules present in the protein. It's the way of having H pluses going around, but it's anyway a proton transporter. H3O plus is a way of protons being able to interact and be involved in all these equilibria. It complexes ions. It's a constituent of biological macromolecules, so it really is extremely, extremely rich. And on top of that, it is what is what I could call a molecular matchmaker, if you want to, because it is helping in these compounds being able to go together. So it is truly unique. So water as a solvent has these characteristics that no other solvent has. So it is highly unlikely, I can't prove it, it's not said, but because of these characteristics and all these elements I've tried to convey to you today, that it's really highly unlikely that life could emerge in another solvent than in water, which justifies, which explains why NASA is always going for search for the water when they are doing their searches for life on other celestial bodies than on Earth. But to finish off, I'd like to finish off with a quote which I think is extremely important in the context of the school by Albert Eschenmoser, a Swiss chemist who said, "The origin of life cannot be discovered, it has to be reinvented." So what I'm showing to you over here is just giving you scientific facts, scientific information, which might help in trying to see if a hypothesis is plausible or not plausible. I'm in no way pretending to be able to give you any answers to what the origin of life was. Can only contribute in a way of saying you have to remember there are certain scientific facts. You mustn't shut your eyes to those. So it's extremely important to remember that. And then in conclusion, in acknowledgements, apart from the funding bodies, I do want to thank my two close colleagues with whom we debate, including the more philosophical question of do we need a definition of life and what is the definition of life, and is looking for the origin of life a science or it's just a story. We can talk about that over coffee. It's Jacques Reis and Gilles Proylaens, and then these are two PhD students among the other numerous PhD students we have who in their PhD both were interested in questions related to what I've talked today. Emanuela about the hydrophobic effect and Sophie van den Busch about the possibility, and Uwe might know some of the stuff we did there about looking at circularly polarized light and chiral molecules. And thank you very much for your attention.